So I'm doing problem number 52, which says draw a molecular orbital energy level diagram and determine the bond order expected for each of the following diatomic species: diatomic boron B2, B2 minus, B2 plus. State whether each molecule or ion will be paramagnetic or diamagnetic. If it is paramagnetic, give the number of unpaired electrons. So to start, part 1, they're asking for the molecular orbital energy diagrams, which are showing how the electrons are paired in the sigma and pi bonding orbitals. And so we start by at the 2s orbital, and we don't include the 1s orbital because it would make our diagram too long. Usually you'll see that most molecular orbital energy diagrams only include 3 bonding orbitals and 3 anti-bonding orbitals. That's just not because of a technical term, that's just to make sure it takes up less space and you can still get the justification of it. Usually you want to include all the way up till the very end, like where there's no more electrons, and not do something in the middle. Like I wouldn't want to start with just the 1s and 2s because I wouldn't be able to see the ending, which would be the 2p for boron. So the first thing we need to do is calculate how many total electrons are in our molecule, or in this case our diatomic atom, or diatomic molecule boron 2. And that would be 10 because boron has 5 electrons plus its second boron, which would be another 5. So that'd be 10 total. Boron 2 minus would have 11 electrons because the minus indicates a gain of an electron. And the boron 2 plus is the exact same, except it's now taking away an electron because the plus indicates a loss of an electron. So now there's only 6 left because we're not including the 1s orbital, which would include 4 electrons. And 4 electrons would be the 2 in the sigma 1s orbital and the 2 in the antibonding sigma 1s orbital. And so if you take those 4 away off of the 10, you have 6 left remaining, so we're only going to fill in 6 onto our energy diagram. So 5 and 6 would go into the sigma 2s, 6 and 7 would go into, 7 and 8 would go into the antibonding sigma 2s, 9 would go on the left side of the pi 2p, and 10 would go on the right side of the pi 2p. Now the reason that there is 2 sections for pi 2p is because pi orbitals need to have a higher amount of electrons because they have a higher energy capacity to completely fill the orbital before you can move on. So we fill in half of each pair because you can't fill in one pair of the sigma 2p, the pi 2p, because it would make it uneven and unbalanced. So we need to fill in the half and then start pairing them off. And this is whenever we can start pairing them off because there's 11 electrons. And so it's just like our original 10, but now we're adding one. So we add another electron to the left side of pi 2p to complete that pair. And now we'll have a total of 11 electrons because this will be 7 including the 4 in the 1s orbitals. Lastly, C, it's 9. All we're doing is taking away an electron from our original A, which would be the right side, and then you're left with 9 electrons. So now we need to determine if A, B, and C are paramagnetic or diamagnetic, and we can do this by using the bond order formula. The bond order formula is the number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals divided by 2. Now we need to remember that bonding orbitals are indicated without the asterisk on it. So whenever you're trying to count up how many electrons are in bonding orbitals, you want to look at the sigma or pi that doesn't have an asterisk near it. If it has an asterisk near it, you need to count those up for the anti-bonding orbitals. So if we look at A, we can see there are 4 in the bonding orbitals, which is 2 in the sigma 2s and 2 in the pi 2p, and there are 2 in the anti-bonding orbitals. So that would be 4 minus 2 divided by 2 is equal to 1. Therefore, A is paramagnetic because the bond order is not equal to 0 So that means there's an unpaired electron in the molecule. So for B, we do the same thing. There's 5 in the bonding orbitals, 2 in the sigma 2s, and 3 in the pi 2p. And there's 2 in the antibonding. So 5 minus 2 divided by 2 is 3/2. Therefore, B is going to be magnetic because the bond order is not equal to 0. And for C, there's 3 in the bonding, 2 in the antibonding. So 3 minus 2 divided by 2 is 1/2. Therefore, C is paramagnetic. Now we need to determine how many unpaired electrons A, B, and C have. And since they're all paramagnetic, that means they're all going to have a unpaired electron somewhere, and we just need to find exactly how many there are. We can do this one of 2 ways. The easiest way, in my opinion, is to look at the diagrams we just made and count how many dashes with a line there are, or electrons, and see how many don't have its pair. But for this, we're going to be using the bond order values. So the rules for bond order values are, if it's a whole number, there's going to be 2 unpaired electrons, and if there's a half number, like a 3/2 or 1/2, which is what we got, there's going to be 1 unpaired electron. So for A, the bond order value is 1, so therefore there's going to be 2. The bond order value for B is 3/2, so it's going to be 1 unpaired. And finally, C has a bond order value of 1/2, so there's going to be 1 unpaired electron.